Now that we have compared some statistics by domain, let's take a look on how to manage outliers and apply capping. RMSP does offer more advanced tools to perform capping, including local capping with local search and local criteria. For this example, we are only going to apply global capping by domain, and we are only going to perform some basic outlier analysis based on probability plots. To perform the capping, we start with certain parameters. In this case, we are selecting as a starting point a percentile which is specified for each domain. So we have this percentile dictionary with the 99.9 percentile for the outside and also the same percentile for the inside domain. Now what we need to do is to calculate for each one of these domains, for each one of these distributions, what is the respective value of gold that matches that selected percentile. So for that, we are creating an empty dictionary, and then we are looping over the domains. We are getting the indexes of all the composites within that domain using the domain.getKeyout. So this results in a mask array, which we can use with .lock to query all the points inside that domain. And then we are using the function .quantile and providing the quantile for each one of the domains. And the result of this function will be the gold value of that selected quantile. And then we are saving that gold value into our capping dictionary. So let's run this cell and see the result. As you can see, for each one of the domains, I'm selecting a certain grade which represents the 99.9 percentile. We can now visualize that selected capping value against the gold distribution. So for that, what we are doing is to create an empty figure with one row and two columns. And right here, we are just setting some minimum and maximum values for the distributions. And we are iterating over the domain and the axis. Because we have two domains and two axes, we can use zip. And zip will combine each one of the domains with each one of the axes. Inside the loop, we are getting a slice of the composites with the domain.getData. And with that slice, we are running the probability plot for the gold variable and adding that to the respective axis. We are not showing Tucky colors because sometimes Tucky colors are not helpful. So that's the case in this scenario. And we're setting the title of the figure to the domain. And we are also controlling the X limits based on the variable minimum and maximum value. This will generate a probability plot, but we want to see more. So what we're doing here is to add a vertical line to the figure at the capping location. And we are also labeling that line with the capping value and also adding the legend to the figure. So let's see the output. So for the first axis, we are plotting the probability plot for the outside domain, and we are highlighting the selected capping value for the outside domain, remembering that that should match the probability of 0.999 which was the selection above. And we do the same thing for the inside domain. We have the probability plot, and the selected value matches the 0.999 probability, which gives us a capping value of 28.8. Of course, this would be a starting point, and then by looking at the probability plot, you might look for discontinuity or inflection points in order to assist the definition of the outlier and what the reasonable capping value is. And also, of course, reconciliation with production data at the end will also assist you on defining a capping value that improves the reconciliation. But assuming that our selection is reasonable, we can now go ahead and apply the capping values. We do perform capping by domain. So the first thing is a loop over all the domains. Then inside my loop, I have the cap transformer, and I'm initializing the cap transformer by using the .fit method. And the .fit method will require us to provide, in this case, the value, the threshold for capping. So we need to specify that we want to cap everything that's greater than, and then our capping value. And we are capping to the same value as our capping value. Another option with the cap transformer is to perform a lower tail capping. In that case, we could specify less than, and then our lower tail capping value, and then capping 2 is the number that will replace the capped value. So this will initialize the class, and we can now go ahead and apply. But because we are performing that operation by domain, we get the data or the indexes of the data for the particular domain that we are looping over. And we use those indexes with the .lock function to select that data. And because we are doing that capping for the gold variable, we select also the column gold variable. And we use the capper .transform for transforming our data. So notice that we are using the same column name on the output as we are in the input. That means that after I run this cell, my gold variable will be replaced by the capped variable. Sometimes it is desirable to keep a separate name if in the future you need access to the original value. But in this case, we are fine with overwriting the original gold values. So we do that when we apply the capping. So after running this cell, my composites are now capped. Now we can see how the capping impact the statistics of our data. Now that my composites are capped, I can call the same unique compare object by cat using my composites and gold variable. But now we save it in a different object, unique comps underscore cap, and we can see the statistics. So this is the table with the summary statistics with the capped variables. However, we might want to see it side by side with the uncapped. So for that, we have a utility function within the parameter file, which I can talk about after we run this cell, where if I provide one unique compare object and then a second unique compare object, it will generate a comparison table. So if I run this cell, the result is for each one of the domains outside and inside, and for each one of the statistics, I have the original and the capped. So we can see the impact of capping on the mean. So the original was 0.36 and the capped is now 0.35. And we can do the same inspection for each one of the output statistics.